and welcome to the third edition of the NTNU Energy Transition Seminar Series. Today, we turn our focus to a transformative and highly relevant topic: hydrogen export from Norway. Opportunities and challenges. Hydrogen is increasingly seen as a cornerstone of the global energy transition, offering a pathway to decarbonize hard-to-abate sectors. For Norway, with its abundant renewable energy resources and established energy infrastructure, hydrogen export presents a significant opportunity. However, alongside this promise come critical challenges, including scaling production, ensuring competitiveness, and navigating global market dynamics. Our goal today is to explore these aspects and assess Norway's potential to become a leading player in the hydrogen economy. For those who have not met us before, I'm Benjamin Mitterutzner, researcher at the Department of Industrial Economics, and I'm joined by Vivian Ober, PhD candidate at the Department of Electric Energy. Together, we will guide you through today's discussion, with Amber giving us essential support behind the scenes. So thank you all for being here. And before we get started, I wanted to apologize to the online audience. We had some technical difficulties, but I hope you can follow us because I know there are plenty online. Thank you very much.
Thank you, Benjamin. And thank you all for coming to this new edition of the seminar, the Energy Transition Seminar. So what we aim to do with this seminar is to create a platform where participants can learn about ongoing research projects, expand academic networks, share energy-related expertise across departments, and holistically approach the energy transition. So today we're very happy to welcome Julian Strauss and Alessandro Campari to share their expertise on hydrogen. So Julian will start by exploring the exciting opportunities for hydrogen export from Norway and how it can contribute to the energy transition. And afterwards, Alessandro will take us on a deep dive into the intricate details of hydrogen engineering and safety, shedding light on the technical challenges and solutions shaping this industry. Afterwards, we will have a Q&A with a discussion involving all of you here today, and we hope to have active participation. And don't forget to stick around afterwards for pizza and socializing. We look forward to connecting with all of you.
Thank you. Indeed, we are delighted to introduce Julian Strauss. He's a research scientist at Sintef Energy Research. With a strong foundation in chemical engineering, Julian holds a degree from ETH Zurich and a PhD from NTNU. His expertise lies in process modeling, energy system modeling, and hydrogen production, making him exceptionally qualified to share his knowledge on today's topic. Julian, we are excited to hear your insights. The floor is now yours.
Thanks for the introduction. I hope you can all hear me rather well, also the digital attendance. I'm going to talk today about results which came from a research project at Sintef Energy. The project was called Clean Export, and we looked into export opportunities from Norway into Europe and decarbonized export opportunities. The overall aim of that project was that we utilize techno-economic analysis. You won't see too many assumptions or numbers from me today on screen because you have to do a crazy amount of assumptions if you're going to model the future after 2040. So in that respect, I try to focus more on the key takeaway messages we can receive from these analyses. Now, why do we actually talk about hydrogen export? Norway could also use hydrogen domestically. There's a demand there. And there's also actually quite a lot of projects ongoing. To give you a few of the projects we have or we are involved in, we're looking into the decarbonization of silicium and manganese project and production in the Mikala project led by Sintef Industry. It's a crucial project because their emissions are not due to energy usage. It's because you need a reducing agent, and the reducing agent is unfortunately coal. There's also the ammonia fuel bunkering network project, which is finishing now, which was looking into developing ammonia as clean fuel for mostly offshore supply vessels, and also especially looking into the bunkering infrastructure, so both safety of ammonia, but also how you can transfer ammonia from a bunkering terminal to the ships. And the last project is a so-called sail schist project, which Sintef and Antonians involved there, and that is looking into hydrogen as a fuel for fishing vessels. When you take a look at these three different projects, you can see directly also the focus in Norwegian projects. It's about decarbonizing industry, and specifically the metal industry, and decarbonizing transport sectors. And why is it that? If we take a look now at a few numbers, you have to take a look from Ryan. If we take a look at the plan of the European Union in the REPower EU project, they need to have or want to import close to 400 terawatt hours higher heating value hydrogen, just 10 megatons a year. For Norway, if we take a look at the net inland consumption, so pretty much what is consumed in Norway, except for energy as a resource, it's only 280 terawatt hours, and the majority of that is actually covered by electricity. So the Norwegian energy system is heavily decarbonized, except for transport and industry, and specifically the metal production industry. Another number coming in here is the net inland excess, which also translates how much energy is consumed by the energy producing sector. So in this case, offshore oil and gas. And the interesting point here, you can see it already because it's building its way around that. The total exports of Norway in energy is about 2,200 barrels. All the numbers are averaging 2050 to 2090 to avoid impacts based on corona and energy prices starting in 2020. So Norway is a country which is currently gaining crazy amount of money through fossil fuel exports, and obviously that has to be decarbonized. And hydrogen is one opportunity for that. To give you here also a few numbers on top for these ones here, the electricity demand in Germany in 23 was 460 terawatt hours, France 450. So we're talking here about large scale numbers, and Norway can actually produce quite a lot of. Now, hydrogen can be exported in two ways. Let us first look into pipeline gas exports. For pipeline gas, we did actually quite a lot, hundreds of simulations to look how it can develop from 2030 to 2050 based on different demands, areas, and so on. The numbers really, the exact numbers do not matter. It's what you can take out of it. And here's one example from a case study which we did. Looks rather simple, but then again, we need a lot of primary barrels, making it a bit more complex. And that is looking for hydrogen export infrastructure to Germany. That reason for that is because Germany is most likely one of the largest demand country for hydrogen. Oh, yeah. Anyhow, the interesting point here to note, three things are important to note on that, not on the figure, but based on the study. First of all, the hydrogen exported from Norway includes both natural gas refining with CO2 capture, so-called blue hydrogen, and electrolysis, green hydrogen. It starts with initially blue hydrogen, later on transitioning to green hydrogen based on the boundary conditions and the cost which we assume. But actually, the more important part is these pipelines here. You can first of all see we have two pipelines. The size of the line corresponds to the size of the pipeline. These are modeled using economy of scales, non-linear cost functions. And a key factor here is we want to implement as few pipelines as possible. We have here the two on the left and on the right. In addition, because you also want to produce in Norway 5 in between. But we have two pipelines, and these two pipelines are invested at the capacity which is required in the later stages. So if you have a demand in 2030 of 5 gigawatt or 3 gigawatt continuously, then even then you try to invest into a power plant which has a size of 30 gigawatt because you won't have the long term or you want to exploit economy of scale. You're not investing every single year in a new power plant based on increased demand. Secondly, it also shows here, given a certain hydrogen demand, we can easily export up to 180 terawatt hours in 2050. Natural gas is available, power is a bit of a different question, but it's possible. Now, the country where you export to is really not relevant. These studies where we just look into profitability exporting to the United Kingdom or to Germany, the difference in prices, starting from the left to the right picture, is about 1 to 2 euros per megawatt hour. The full uncertainty we have in the analysis in every single parameter is significantly higher than. So what does that imply? First of all, we need to export large quantities because otherwise power plant infrastructure doesn't pay off. And secondly, you won't have a guaranteed large demand potentially because you have to build up the demand in the long term. Now, another frequently discussed topic, and specifically by people who have no understanding about process control, is somehow it's exporting liquid form. You can export hydrogen in liquid form, in form of ammonia, and in the form of liquid hydrogen. Both processes are energy-wise rather similar with respect to how much you need. However, you need more hydrogen for ammonia production because you have losses due to the exothermicity of the reaction, while you need more direct electricity if you want to produce liquid hydrogen. And in this case, we were looking in northern Norway because northern Norway is currently in the only part of Norway where you export liquid energy in the form of LNG from Mercury. In this study, in this figure, it's a bit complex. It shows you the different regions which we have. Now it actually has precise numbers. The coloring it, the darker the blue, the more electrolysis investments you have in this region. The numbers on the lines are pipeline investments, and we allowed here to export hydrogen both to northern Sweden for the metal decarbonization and also to the global market. And in this case, we considered liquid and hydrogen, ammonia at the gate of the factory. One thing which is clear from this next figure, green implies wind investments. And the darker the cover, again, the more investments. You need a crazy amount of renewable energy if you want to export that. We're pretty much here, always capped at the maximum we allow for the individual regions. That has to come through. I'm not going into the full discussion with respect to whether it's feasible or not. I'm just saying, if you want to export either liquid ammonia or liquid hydrogen from Norway, then you can't circumvent Australian power investments or increase in renewable power generation. A second interesting point from this figure here is, and it's very difficult to see based on the numbers, but you can see that the hydrogen production is pretty much centralized where they want to go from, while the renewable power generation is invested everywhere. So that allows us to say for the hydrogen pipelines that if you go for really small pipeline size, the transmission infrastructure sizes, you don't build a pipeline. Small pipelines are ridiculously expensive relatively compared to large pipelines. So in that respect, economy of scale is playing a major role. So you only have here the investments in these three regions in electrolyzers because you don't want to invest in it. Now for the power lines, there's a bit of an assumption again, boundary conditions. We assume that you do not have economies of scale, which is obviously not true. But the question was frequently done in the modeling. So in that respect, it prefers to invest in power lines to get to a centralized location and then invest there into electrolyzers. Now, an important point is as well that exports happening both in liquid form, so liquid hydrogen and liquid ammonia. And that boils down again to the difference in electricity demand. We have here natural gas reform with CCS also included, and that is thermal energy natural gas versus electrical energy. So for liquefaction, you need more electrical energy, while for ammonia production, we need more thermal energy. And you try here to maximize the overall profit. Unfortunately, for northern Norway, you need rather high hydrogen prices or ammonia prices on the global market that we actually start exporting. because if the prices are too low, there's no reason to do. Now, now I was just talking about two case studies specifically done for the hydrogen export from Norway, but from Western Norway, Northern Norway. And why is it not happening? If you have followed the news in Norway in recent years, you have realized that you have news hydrogen pipeline put on the ice, hydrogen hub put on the ice, ammonia production for whatever put on ice. Um, Hydrogen currently is again in its typical cycle. It's going down, implying that we have significantly less possibilities for recycling of love, which is not too nice for me because that is how I make my living. But anyhow, what are the challenges for that? And the key factor is actually energy availability. If you recall the figure which I showed in the beginning, where we had the hydrogen imports the European Union want to have compared to electricity production in Norway and in the other countries, you can see that you need a lot of energy, and hydrogen is really not the efficient approach. You have transformation steps, be it via electrolyzers or via natural gas reforming. If you do not use hydrogen directly, but instead use it, so you have again meltdown. And since summer 21, there is an energy scarcity here. So in that respect, obviously, if you didn't have energy, why use in conversion processes? But energy scarcity even more translates to energy prices. For those of you who live here in Norway, free price and biddings, you're not really affected too much by it. We've seen oil prices and so on. That does not really matter. And power prices are, I think this year, averaging 20 euros megawatt on limit of that. But in southern Norway, in Germany, in France, in the UK, so pretty much all countries in the south, you have crazy high energy prices, which obviously, if energy is expensive, why use in conversion processes use it direct? And the natural gas prices also again drastically increase. I checked it today at TTF, it's sitting at 50 euros a megawatt hour after having a minimum of 28 in the beginning of the year, and pre-Russian invasion had 20-ish averaging. And also now point is the CO2 price. It's way too low. We're currently sitting today, again, check that, 68 euros a ton. If energy is expensive, you pay little for emissions, uh, and you do not have sufficient energy, it's a major issue. Now, all of these challenges are not related directly to hydrogen production in Norway or export, but it has indirectly an impact for Norwegian hydrogen export because, as I mentioned beforehand, you need economy of scales. If you want to export hydrogen from Norway to Europe, you need to go big. If you don't go big, don't bother doing it. Because the pipeline which really transports 2-3 gigawatts offshore pipeline that is significantly too expensive. It's really cheap if you have a 13 gigawatt pipeline, but a 2 gigawatt pipeline does not really pay off there. And that also translates to you need a hydrogen demand. So you need a projected hydrogen demand in the countries, and a lot of people will disagree with me, but except for refineries, you do not have a hydrogen demand today. Ammonia and methanol production is not a hydrogen demand, it's a synthesis gas demand. So a mixture of nitrogen, hydrogen, or CO hydrogen. And that implies also that these processes have to invest a lot in addition to be able to use pure hydrogen from another. And with that, I'm seeing that Vivian is holding out that I should conclude, and I think I answered the. Thank you for your attention.
Thank you very much, Julian, for this very insightful presentation. Yes. So we look forward to discussing all the topics you brought in your presentation later this year. But for now, we have Alessandro's presentation. So Alessandro Campari is a postdoctoral researcher at the Department of Mechanical and Industrial Engineering at NTNU. He just finished his PhD last summer, which he took at the same department. So the title of his thesis was Loss Prevention and Operational Safety, a risk-based inspection approach for hydrogen technology. So I think we'll be in good hands to discuss hydrogen safety issues. I now hand over the floor to Aldo.
Thank you very much for taking an introduction. Today, my purpose is to give you an overview of the safety issues associated with hydrogen technologies and also some methodologies to address those issues through preventive maintenance approaches. So, as you all know, hydrogen has been widely indicated as a promising energy vector to mitigate the actual values sectors from road transport to maritime sector, shipping, but also aviation and aerospace, and some industrial sectors such as steel and glass manufacturing. Despite the inherent environmental advantages of hydrogen as an energy carrier, we have to address many issues related to safety that somehow hinders its widespread rollout. So, considering that hydrogen is a highly flammable substance, it is crucial not only to address the releases of hydrogen, but also to prevent those releases by avoiding any component failure. So, a very common approach in safety science is to analyze previous incidents and accidents in order to avoid similar events in the future. And that's exactly what we have done at the beginning of our research. So we investigate previous events, observed events, that are collected in the High 2.0 database developed by the European Commission. And we figured out that basically 1/4 of all the collected incidents associated with hydrogen are due to material failures. So basically component breakdowns. And then we try to figure out how many incidents are unequivocally associated to the degrading effect that is due to hydrogen on the components. And we noticed that 7% of the total are actually due to environmental degradation due to the aerosol exposure. So the vast majority of such events could have been prevented through proper inspection and maintenance strategies. And therefore, we focused on this approach to guarantee the safety of hydrogen technologies. But before going on with this methodology, I would like to give you a very brief overview of hydrogen enrichment, an environmental degradation that results from the interaction of in a hydrogen-containing operative environment, a material that should be susceptible to this type of degradation, but also the application of a mechanical load. When all those factors are combined together, materials can be degraded, and this degradation manifests itself as a reduction in various mechanical properties. First of all, there is a loss of ductility of the material, and this degradation applies to the vast majority of steels that are commonly used for engineering applications. Second, we have a reduction of fracture toughness, which is very important in the case of impact with external objects. And last but not least, there is a significant increase in fabric rate. And all those degradations together result in a lower expected lifetime of regular components and quite often in unexpected failures. So a common approach to avoid the loss of integrity of industrial system is using preventive maintenance approaches. And among the various strategies that are widely used in the industry, we focused on this one, which is quite recent, that has been developed for the oil and gas sector, and it's called RDI, that stands for risk-based inspection. It is based on the assumption that risk is not equally distributed among the components of plant, and therefore, it is better to focus our inspection effort and our inspection associated expenses through the components that are considered high risk. So by addressing this component more carefully, we can mitigate the overall risk of the plant and achieve the greatest benefit at the lowest possible cost. Well, this is the best flow diagram of the MBA approach. It starts from the data collection, and then from the specific characteristics of the data, we could calculate the probability of failure through this very simple formula and investigate also the consequences of failure for different bolt sizes. So we can imagine that we have a release from a certain component, say a compressor or a pipe or whatever, and we can simulate the effect of a hydrogen release. By combining probabilities and consequences of failure, we can calculate the risk. That is basically a product of those two factors. We can rank our component based on this risk level, and the company structural band is tailored for the plant, and also can mediate the risk associated to the device components by focusing on the most risky ones. After that, and after implementing our inspection strategy, we will gather other information about the plant status and conditions, and reassess the model. So this strategy could at the same time reduce the probability of failure, mitigate the consequences of failure, and it's a separate methodology. So it tends to improve itself iteration by iteration. This strategy is potentially applicable to a wide range of components, from big steel reformers to pipelines, gas cylinders, and components for liquid hydrogen and marine storage. So in order to implement this strategy for hydrogen technologies, it's important to gather data about the components and also the materials we're using in our plants. And considering the high interest towards hydrogen transfer pipeline, during my PhD, we focused on the investigation of pipeline steels, and we conducted tensile tests on material that is commonly used for the existing natural gas pipeline infrastructure. We used, let's say, pretty conventional testing strategy that is very simple to handle and reproduce compared to the state-of-the-art approaches. Way less expensive, way cheaper, and it has little safety concerns. On the other side, I have to mention that the results obtained with this testing approach are quite scattered, so the reliability might be questioned. So yeah, during the experimental campaign, we manufactured the specimens, so those little piece of metal with a hole inside, and we compressed hydrogen in the inner pole in order to mimic somehow the real operating conditions of our equipment, and more specifically of the pipelines. We manufactured those specimens with two different techniques, drilling and reeling, in order to achieve two different surface toughness in the inner pole, and to figure out what is the impact of the inner surface of the fence on the susceptibility to hydrogen enrichment. We considered a very high purity of hydrogen and operating conditions that are quite close to the real operating conditions of pipeline. So high pressure, approximately 60 bars, and near room temperature. We used simple bottles to fill the small hole with compressed hydrogen. So considering the operating pressure, we didn't need a compressor. And here I would like to show you some results of our experimental campaign. On the upper part of the slide, you can see the specimen that we tested in, let's say, inert environment. We used ambient air. And you can see from the factor gravity analysis that there are ripples, so small poles, that indicate ductile behavior. But if we go to the specimen tested in hydrogen, well, in this case, the factor gravity appearance is completely different. And you can see this structure move that is known as quasi-cleavage structure and indicates a very ductile behavior. You can imagine that this brittle behavior has impact in terms of safety of the equipment. In this slide, you can see the stress inputs, and you can see the lines in length correspond to tests conducted in an inert environment, and the lines in red and blue correspond to tests conducted in a hydrogen environment. And you can see that the specimen tend to fail earlier, basically, at a lower nominal strain rate. So we can figure out that those components will be immediately less reliable in the field. Here there is a summary of our results, and from this graph we can see that basically there is no substantial impact considering a blinkered steel, so a very old steel manufactured maybe 30 years ago, and a modern steel. But there is quite a strong impact when we investigate the effect of surface finishing. So the more rough the surface is, the more susceptible the material will be to hydrogen enrichment. Unfortunately, when we investigate pipelines, we can expect a very high roughness. Therefore, they will be highly sensitive towards hydrogen return. After gathering experimental data, we tried to develop machine learning models, so level-driven models, in order to predict this susceptibility also for never-seen-before materials and components. So we tried to develop this model and we tested the model on a real test stand. We tried to use 3 different pipelines, old-fashioned one, a large-scale one, and a modern one. They were manufactured in different years using different techniques, so they present way different technical characteristics. And for each pipeline, we distinguished 3 different legs. One downstream of the compression station, the second one in between the compression station and the suction site, and the last one upstream of the suction site. All these legs are characterized by different logging conditions in terms of operating pressures and pressure fluctuations within the pipeline. So, in the case of the section downstream of the compression station, we consider a condition where the average pressure is pretty high and there are sudden pressure drop when the infrastructure is formally not at the design conditions. In the second section, there is a mean load condition. So basically, the operating pressure is lower, but we have smaller fluctuations. And in the last stretch of pipe, we have a condition that is known as overload. So normally the pressure is very low, and there are pressure peaks now and then. After calculating the severity of hydrogen return for these components, we implemented the conventional RBI structure that is depicted in this slide. So a brief overview of our results for this case study. We considered 5 different classes of severity, ranging from negligible to extreme. And we tried to bring this data-driven model. We achieved a very good accuracy of 94, sometimes 95%. So the model was deemed quite reliable in the end. Therefore, we implemented this approach. From the analysis of the features, so the operating parameters that we have considered, we can see that the most important point by far is the so-called stress intensity range, which is associated with the amplitude of pressure fluctuations within the pipeline. As you probably can imagine, a pipeline can operate at constant pressure level, but quite often it is subjected to pressure fluctuation because of the different demand of natural gas or hydrogen in this case over the periods of the year or over the daytime. Another important parameter is the steel grade. So we can see that basically the selection of proper materials for the existing pipeline infrastructure is crucial in order to adapt the existing pipelines for hydrogen transport. In this big table here, we have calculated the probability following this approach. And we have compared the exact same infrastructure used for hydrogen transport in the first case and for natural gas transport in the second case. And as you can see from the numbers in the last column, these are the categories of probability. So basically the probability of failure for every stretch of pipe. We can see that for the vast majority of our pipelines, the probability category tend to increase when we repurpose the pipeline for hydrogen transport. Therefore, the same infrastructure operating under more or less the same conditions, just changing the operating fluid that we are using, result in a substantial impact in terms of safety. So, as I mentioned, same operating conditions, different environment, a very higher probability of failure. Considering on the other side the consequences, we have a completely opposite trend. So even if hydrogen is highly flammable, we see from these column charts here that the consequences in the case of the release from a hydrogen transport pipeline are way lower compared to the consequences of natural gas releases. That's why for the same old size, we will have a way lower mass flow rate in the case of hydrogen because it's a lightweight substance compared to natural gas. So the mass flow is lower, and also the relative heat transfer that is transmitted when hydrogen burns is way lower compared to the case of natural gas. Calculating the consequences for a set of all sizes ranges for a small pinhole up to a full bore reactor of the pilot, we can see that these trends remain more or less the same. And this is mostly due to the lower mass of hydrogen and also the low thermal radiation that is emitted during combustion. So, merging the results of the probabilities and consequences of failure, we obtain this graph here, where the various pipelines added and the various stretches of pipe are plotted in this graph. That shows on the x-axis the consequences of failure, and on the x-axis the probabilities. It's in a double logarithmic state, but you can see that basically pipelines for hydrogen transport tend to have higher risk of failure earlier, and this is mostly due to the increased probability of failure due to hydrogen embrittlement. Of course, we try to mitigate this risk, and we developed inspection plan for each stretch of pipe, and we see that the pipelines that are old-fashioned and that are used for hydrogen transport, and particularly the section that is downstream of the conventional station, need more frequent and more extensive inspection activities. Last but not least, we have to say that in order to mitigate the risk of failure due to the only way we have is changing the operating conditions of the pipeline. So basically reducing the pressure fluctuations and reducing the nominal operating pressure of the pipeline. If on the one hand, by doing that, we can obtain positive impact in terms of safety, we will have an negative environmental impact because we will transport less hydrogen, and also a very bad economic impact for the infrastructure because it will be able to deliver a lower amount of fuel. So that's it so far. If you have any question, I'll be very happy to answer. Thank you.
Thank you very much, Alessandro, for a very captivating presentation. And I think you can both come on stage for the Q&A session, which follows now. Maybe I start with Alessandro. I have a quick question, and then I have one question for Julian, and then we hand over to the audience. At the last slide, lower hydrogen pressure. In which range are we speaking here then? Because is it 30 bar or, well,
You have it's very difficult to give a short answer because according to standards, the maximum allowable pressure for hydrogen transport infrastructure is around 60 bars. That's why we have tested our steel at 60 bars. Nevertheless, there are a lot of researchers that consider this threshold just a nominal one. So there is no technical reason to set these strict limits. So they are trying to expand the field of applicability of hydrogen pipelines up to 100 bars with different types of seals. But it's quite important not only to add defined pressure that be lower than 100, but also lower than 60 bars. But most importantly, we have to decrease the amplitude of pressure fluctuations. So we can, at certain point, operate the pipeline at 60 bars. But we cannot have pressure drops higher than, let's say, 10 bars in amplitude. So the pipeline can operate between 60 and 15. And this is way better than operating pipeline at a lower average pressure at with higher pressure fluctuations. So let's say from 30 to 1.
Okay. Yeah, thank you. And for Julian, I have a question because I know he's very good at costs of hydrogen production. And I've read a paper recently about mitigating emissions from the steel industry from the MIT guys, Benavides et al. And they have told that, for example, blue hydrogen, emitter reforming with CCS or autothermal reforming with CCS, they have around $2 per kilogram cost of H2 production. Now for the green hydrogen, via an electrolyzer, it's 3 times more. What is your opinion? Is this one-to-one transferable to European standards? Probably not.
actually cost of hydrogen is a hot topic. If you have 5 researchers in a field working or in a room working on that, you have opinions. The key factor for everything which is related to cost is what you assume, both for your energy input, because for natural gas reform with the CCS, the major cost factor is actually the natural gas. If we assume the prices of 20 euros a megawatt hour or 60 euros a megawatt hour for natural gas, it has a major impact. So it's one work we did pre-2019, we ended up at around 170 euros per kilogram delivered to Germany. For green hydrogen, it's even more difficult to say anything about that, because for electrolyzers, you have on top of that how you operate it, how much electricity price fluctuations you have, whether you want to participate in the day ahead, in the intraday market, on the reserve market, and the capital costs very much play a major role. But if you assume electricity price times 1.5, that is the minimum price you have, current electrolyzer technology, and capital costs, hard to say, but it's currently quite high. That I can.
Thank you very much. So, any questions? Yeah,
Maybe just a few instructions. So please keep it short when you ask a question. And also, it's nice if you can manage to try to frame your questions so that they are addressed to both our speakers. But yeah, most important is just that you participate. So if you have a question, just raise your hand, and Amber will send you the cube microphone.
Oh, thanks to Zurian and Alexander very much for the great talks. So if you can indulge me in a pre-mortem exercise, if we are in 2035, hydrogen just really didn't work out. Maybe only 5% of all projects planned were actually went ahead. If we're in that future and you try to look back, what happened wrong? What was the problem?
So what's up? Now, speaking personally, not any of you are centered in that point because it's important. In my personal opinion, hydrogen is a solution which is by no means in any applications the best solution, but it's a solution which we need to use if we want to decarbonize. So if if you have a project which looks into car refueling infrastructure, I'm fine. If it's long distance trucks transport, then most likely battery electric is better. Entirely okay. If you say something is wrong with respect to the parts where you actually need hydrogen and it's not coming there, then I would say that the core reason why I would not have come in is related to pretty much no one thinking about keeping the cloud process, because I don't see necessarily a way how it can go to decarbonization without hydrogen, and that is there to some degree necessity. But then again, looking at the last COP, I'm quite certain anyhow moving in that direction.
Some more other thoughts.
But on the strategy, I think that one aspect that could go on is the lack of trust from the public. So imagine to have an accident or an incident with a very widespread technology like oil and gas or whatever. Probably this incident will not impact the trust of the population toward this technology because it has already been accepted by the public. But imagine to have the exact same incident with the same impact in terms of economic loss, human losses, or whatever, with technology that is under development and not really widespread. For sure, this technology will be considered immediately unsafe by the public. And this was the case, for instance, of the nuclear power. So just to make an example, after Chernobyl, the Chernobyl incident, we had a referendum in Italy because people have completely lost trust towards nuclear power, regardless of the potential, regardless of the very low environmental impact. So if there is a lot of trust of the population and of the industrial stakeholders for a certain technology, for sure it will not be used. And in order to have trust, I think it is important to guarantee a safety level that is not only comparable to the conventional technologies, but even higher. Yeah.
Very interesting. Any other questions through? Yes.
Thank you for the presentations. I was wondering, what is the advantage that Norway has to export green hydrogen? And why would Germany import from Norway green hydrogen?
Yeah, there are multiple reasons for that. First of all, I'm German, so I'm not pushing them should export to Germany because of that. But I have a bit of an understanding of the German energy system. There are currently in Germany, you can't really produce green hydrogen if you want to have green hydrogen in Germany because you don't have the decarbonized grid. So you need to have the additionality plus temporal and to call it green. Now, why is Norway for green hydrogen quite suited is actually related to the long coastline. The wind power resources in Norway are excellent. The wind park outside at Fusen is producing one of the lowest levelized costs of electricity due to the really good wind conditions. So in that respect, that was one of the initial parts when we developed that project, where we considered it for the renewable energy sources. And obviously, Norway has the easy possibility to kickstart exports due to first exporting blue hydrogen due to the natural gas reform and natural gas reserves and CO2 storage sites. Now, in a country like, or the countries where Norway would export to, either of these countries will most likely remain energy import countries. You don't have sufficient energy resources in Germany. You don't have sufficient energy resources in the UK. And both of them are importing a large amount of fossil energy right now. And that would be the point to provide decarbonized energy to kickstart the whole process.
Well, for sure, the production of energy from natural sources and from renewable sources is immediately stochastic and aleatory. So in order to cover the peak of production, we have to convert this energy somehow. And it's immediately very challenging to store electric energy. So this energy can be used to produce hydrogen that is more easy to store and handle in large amounts. So if we expect to increase our our production of power from renewable energy, we need to have efficient storage technologies and efficient storage methods and diverse storage methods. So one strategy could be using hydropower, pumping water in a hydro basin. And this is a strategy that has been widely used in the past. But actually, it's important to vary. And one option could be using hydrogen and producing hydrogen with this excess of renewable energy. So that's the advantage of producing green hydrogen and exporting also green hydrogen to Europe.
I will allow myself a little question as well. So at some point, you were comparing pipelines having natural gas and hydrogen. So, talking about the possibility of converting natural gas pipelines to hydrogen pipelines. So I was curious. So, is there any research on that topic?
We have projects which was looking about hydrogen export, retrofitting versus building new pipelines. Generally speaking, retrofitting was a rather valid approach. However, it's a rather difficult modeling or to pose your optimization problem in a way that you get meaningful answers. Because just saying that the pipeline retrofit is significantly cheaper, then obviously you're going to use it. So you need to have the opportunity cost of not exporting natural gas included. So you also have there an additional parent, which is finally uncertain for the future. It is a possibility, but pretty much all the studies which we did and my feeling out of when they presented them is that industry is also more interested in new pipelines instead of repurposing. And you also don't have to worry about all connections which you currently have with Europipe 1, 2, and so on. Because if you repurpose Europipe 1, you have to repurpose also some other connections. Same for Europipe 2. It's a fully integrated pipeline network on the shelf.
Any other questions from the audience?
Yeah, I hope that is not completely a stupid question or I missed something in the presentation. But I was wondering when you were showing the scenarios on the map, where could you export to with the pipelines? I was wondering what is really the point in exporting green hydrogen? Because for green hydrogen, you just increase the capabilities for electric energy transmission to the countries, and then they can produce the green hydrogen themselves, which would maybe be a way to go around a lot of problems. Or is there also a water shortage issue in the related countries?
Water shortage is always included as a problem for hydrogen, and it's for all European countries just a bullshit argument, in my opinion, because it doesn't make sense. The amount of water you would need, it doesn't really impact if you do it in Spain, where they have a drought right now. You can have seawater desalination, which requires a fraction of the water energy consumption of electrolyzers. But actually, the key reason is that you have a significant economy of scale at the upper end of pipelines. So you would not build a pipeline for exporting 1 or 2 gigawatt of hydrogen. That is too expensive. As you mentioned, power lines are the better solution, although political impossible in Norway at the time being. Now, you're talking for these points, you have to go large. And at larger volumes, pipelines have 2 main advantages. First of all, it's cheaper. The not used how was it, Nord Stream pipeline, Nord Stream 2, was cost-wise, I think, now the same as the per kilometer as the direct high voltage direct current cable from Norway to Germany at about 20-30 times the capacity. That's point one. Point two is that I'm not an electrical engineer. I get my colleague on the point for that if I'm wrong. As far as I know, you have significantly less energy demands for long distance transport. Yes, compression is expensive, but the same as if you have AC/DC compression plus in the high voltage power lines, and that is 1% of the energy in hydrogen compared to electricity 5% losses, 10. Obviously, you have the losses in hydrogen production as well, but that doesn't play a role there.
Thank you. I was totally not aware that the pipelines are that cheap.
They are not cheap. If you go to Glasgow and say that pipelines are cheap, then they will tell you they are not expensive, and they are for them. But they are no cost factor for the hydrogen in the end. At least no transmission pipelines. Distribution, different story. Large scale transmission, there is no cost factor.
Are there any other questions?
Thank you for the presentations. Very interesting. I think it was Julian who said that hydrogen is on a downturn in popularity. Are there any reasons for this except for the energy scarcity?
I mean, energy scarcity and prices is the core factor there. Now, simultaneously, it's still a major issue with respect to demand. It's a classical energy problem. I wrote yesterday that I think only 1/3 of the electrolysis manufacturing capacity is used because the demand is there for more. But then again, in my opinion, hydrogen is not the best or the best solution for all of problems. It is what has to be done. It's not, we do not use, or at least in my use, hydrogen is not, we don't use it because we love hydrogen. We use it because it's obviously the only solution. And for other technologies, they have, at least in my opinion again, more development potential. So we saw it with cars, battery electric cars. Definitely the solution. You won't see any hydrogen fuel cell electric vehicles for cars. We see now that we have more and more battery electric transports and trucks. So people are still looking for the long distance transport, but you still have a large development potential for batteries. You do not have too much of a development potential for hydrogen applications. So in that respect, it's hard to as well.
Maybe last question I have for Alessandro. So you said that yeah, we had to be careful because we might need even more safety with hydrogen as it's an emerging technology. But do you feel like in the industry or in general, do we understand correctly the safety issues that hydrogen poses, and do we tackle them appropriately?
Well, from my perspective, I think that hydrogen has now some enough better revisions in terms of safety and reliability. But for sure, there is a problem of lack of expertise, not only of the engineers, but also of the operators that actually enter the technologies. So, for instance, we had a chance to visit a banking facility in the port of Kobe, of Japan. And basically, we are adopting the same approaches, the same methodologies, the same safety procedures that are used for liquid refined natural gas. So they are trying to leverage their knowledge of the different fuel for hydrogen because they don't have the expertise with this type of energy carrier. So this is a problem for sure. The lack of training, lack of operational experience that could result in an increased frequency of human errors and also unexpected situation could arise because we don't really know how handling hydrogen instead of other fuels would impact our environment.
Yeah, it can impact also the price of the cost of hydrogen if we have to revise a bit our safety standards. So that could change the assumptions actually and levels as well.
Yeah, for sure, there is a big expense related to the development of new standards for handling and using hydrogen technologies, and also a lot of expenses to investigate safety issues associated with hydrogen storage, transport, and so on. So yeah, for sure, it will impact the overall cost of hydrogen.
So we are coming almost to the end. So thank you very much for joining this discussion. It was very interesting. And you could, is there a last question? Perfect. Emil?
Thanks. So I just wanted to follow up on that discussion because it was very interesting. Touching on a question I had for you, Alessandro, trying to understand to what extent is this a problem for human safety and human lives and simply cost from having to replace the components more frequently? To this discussion, is it that we can make hydrogen as safe as the current technologies like natural gas for humans and it'll just cost more, to your point? Or is it that it's also actually more dangerous for humans at the end as well?
If it's for still dangerous for humans, but we can translate the risk for humans in financial terms. So since risk is a bogey definition, so it's not a physical quantity, we are used to express the risk in terms of dollar per second per year, basically. So we have on one side the probability, this is basically a frequency, and the consequence that could be measured in financial terms or in terms of safety area. But we can translate the effect of a human loss in financial terms. So basically, it's a common metric to use dollars instead of human losses. It might sound terrible because we are giving a price to human life, but it's common approach. So yeah, sure, it's a risk for human lives. Yeah, there are risk of injuries in handling both gases, hydrogen and liquid hydrogen. Of course, it presents different results. But for sure, it's dangerous for humans, and it's not only a matter of financial impact and financial losses in the case of damage of components or plants.
Thank you very much. You want to follow up on this?
I just wanted to it a general point, if possible.
Yep.
Because I didn't want to sound as I'm entirely against hydrogen. I think it's a really interesting topic as well. But if we are not aware of potential risk hydrogen or the hydrogen research may face, then we are pretty much not very good. So that is more cautioning, not that hydrogen won't play a role, but it's important. The risks associated with it, and also the economic risks, and also the data risks. Yeah, if I get phrase it that way.
I think that's a nice conclusive word by Julian and by Alessandro. They are free. So please give an extra round of applause for our two excellent speakers. And before you can all go to our pizza, I just wanted to remind you that next seminar will be the 23rd of January next year at 3 p.m. here at Buva, and the topic will be hydropower, an old technology facing new expectations. Thank you very much for coming here and enjoy the pizza.